Okay, folks. Now, one thing that might pop up in your head as we're going through this is, why is this robot full of pistons? Here's a piston, there's a piston there, there's two pistons here. Hips have pistons, the thorax has pistons. Some of the anti-gravity structures are enlarged because that's exactly what happens in human beings, but there's pistons everywhere. And it may be that we thought, well, that's just a pretty way to do a robot, but we had a specific purpose for drawing out pistons as the controlling device for generating motion power. In other words, they only can do one thing. They can extend and retract. That's all that pistons do. And the extension and retraction of pistons is our source of motive power for everything that happens in the robot. So you can see that this can move in and out. That's what pistons do. They don't really have another thing that they can do. You can put fluid under pressure in this side and it will move it that way, or you can put fluid under pressure on this side and it will move it the other way. There are a series of properties of pistons that we think make them a good item for generating the power of the robot. One of the interesting things about pistons is that they are inherently stable, in that the placement of the piston head inside the cylinder and the placement of the piston rod inside the end cap, because these clearances are tight, this is a structure that does not tend to want to bend or move or distort. And the effect of doing that is, when you use pistons inside of linkages, it frequently converts the linkages into triangular structures. So you have, for example, the foot that can move dorsiflexion, plantar flexion, and the foot itself is rotating around this joint. And when you add a hydraulic cylinder or piston into this configuration, it takes this joint and makes a triangular shape of the solidity of this joint. And triangular joints are inherently strong and stable. That's one thing. Pistons or hydraulic cylinders allow you to take a large amount of force and put it in a small area. We're thinking to run these at 400 pounds per square inch, which means that with the pistons I've shown here, each one of these is going to have an output force of 1,200 pounds, which is a lot of force. In addition, the equipment that generates the pressurization does not have to be located where the piston is, so that you can have a lot of force in this place and have a motor and pump system somewhere else generating your pressurized fluid, so that you can squeeze the pistons into small spaces and have a significant power of output capacity. Arms that can push and lift, and arms that have enough strength to get the robot out of a problem it may be in. But there isn't a motor in here, and there isn't a fuel supply in here. There's nothing in here other than the tubing for these pistons. One of the interesting things about fluid under pressure is that the conversion of burning of fuel into pressure is almost a one-step activity, which increases the efficiency for your generation of power, because you're not converting it from fuel to heat to pressure to rotation to a generator to electricity, bringing the generator electricity out to the motor and having the motor convert the electricity back into mechanical power. Each of those conversion steps is a loss of efficiency. So if you're converting the heat of combustion directly into fluid pressure, that's a lot more efficient. So there's and finally, the inherent motion of a hydraulic cylinder is very simple, so that anybody can look at linear motion of hydraulic cylinders and start building robots. It's not something that's really very complicated. All you have to do is get all the parts to come together and position them so that the motions that you want to have do not consist of parts that run into each other. It's not that hard. This is why we've chosen pistons.